One of the sequences that you are going to repeatedly see in this course is what is called as a geometric sequence, which is a sequence where the first term in the sequence is a, the second term is a times r, the third term is a times r squared, so on and so forth. Now, if you think about what's special about this sequence, well, you will notice that the ratio of any two adjacent terms is equal to r. And so this r is called as the common ratio of the geometric sequence. A is, of course, the first term, and r is the common ratio. An example of a geometric sequence is, let's say, 5, 10, and what should be the next term if it is a geometric sequence? It should be 20, 40, so on and so forth. So that's a geometric sequence because you can see you get every term in the sequence by multiplying the previous term by 2. So a equal to 5, r equal to 2, and of course it doesn't have to keep on going like this. So in this case the sequence might end at 80. So we have 5 terms in the sequence, and the first term is 5, common ratio is 2. Right, so that's called that's a geometric sequence. One place where you may have seen a geometric sequence before is when you do compound interest when you put money in a bank. So for example, if you put money $8 in a bank and the bank gives you an interest of, let's say, let's call the interest as I, then at the end of the first year, you're going to have a times 1 plus I over 100, where I is the interest rate in percentage, right? Now, at the end of the next year, you're going to get interest on, A is the principal, and the amount of money you're going to have in your bank at the end of the first year is a times 1 plus I over 100. So that includes the principal and the interest. And at the end of the second year, you're going to accrue interest on this principal, right? And so the amount of money you're going to have is going to be a times 1 plus I over 100 squared, so on and so forth. And here you can see that the first term is a, and the common ratio in this case is 1 plus I over 100. So this is right. Now in this class, we're going to see geometric sequences quite often, but typically, or maybe not typically, but quite often, we may see geometric sequences where a and r, or maybe one of them or maybe both of them, are complex quantities. So keep in mind that nothing says that in a geometric sequence a or r have to be real. So in general, we are interested in the case where a and r are complex quantities. Okay, so we're going to define the sum to n terms, let's say capital N. So this means I'm defining this to be the sum of capital N terms of this sequence. And we call this as a geometric series. The sum, we call the sum as a geometric series. And what we want to do is we want to find a nice formula for this. And this formula will come in quite handy in the course. And I'm going to derive this formula now. And I think the derivation is very elegant. And even if you, I'm going to ask that you actually memorize the formula. But more than memorizing the formula, if you remember how to do the derivation, you may be able to derive it quite quickly if you forget the formula for some reason. So the idea in computing the formula is this. Suppose we take this sequence, this series Sn, and we multiply this by r. So we're going to multiply every term here by r. So what do you get when you multiply the first term by r? You're going to get a times r, right? So what I'm going to do is I'm going to write it just below this a times r. So this was obtained from the first term here. Now when I multiply this term by r, I'm going to get a squared, so on and so forth. And when I take the last but one term, which is a times r to the n minus 2, and I multiply that by r, I'm going to get a times r to the n minus 1. And then when I multiply the a times r to the n minus 1, I will get a times r to the n. Right? So if I subtract r times Sn from Sn, so let's subtract the second equation from the first equation. See what happens when I subtract the second equation from the first equation. On the left hand side, we're going to get 1 minus r times Sn. Notice what happens on the right hand side. Something nice happens on the right hand side, right? So when I subtract this from here, these two terms cancel each other out. These two terms are going to cancel each other out, and every term here except the first term in Sn and the last term in r times Sn are going to cancel each other out. And so we're going to be left with simply a minus a times r to the n. This tells us that a nice formula for Sn is a times 1 minus Rn, r to the n divided by 1 minus r. And again, just to emphasize, a and r do not have to be real. They could be complex numbers, right? Everything I've done here works regardless of what a and r are, except when r is equal to 1. So if r is equal to 1, then of course I have a problem dividing by 1 minus r. But if r is 1, it's rather easy to sum n terms in Sn, right? So this formula is true if r is not equal to 1. But what happens when r is 1? If r is 1, the sequence is simply a, so on and so forth, and we're just going to add n such terms, and so Sn is simply going to be equal to a times n if r is equal to 1. So then the formula for the sum of the first n terms of a geometric series is given by a times 1 minus r to the n divided by 1 minus r if r is not equal to 1, and it's given by a times n if r is equal to 1. That's a nice and simple formula, and I want you to remember this formula. So we just derived a formula for the sum of the first n terms of a geometric series. And let me try to write that formula just one more time. But before I do that, I want to caution you about one thing. So we said that a geometric series has a first term a, and then the next term is a times r, the next term is a times r squared, so on and so forth. So notice that the first term is a times r to the 0, right? So the nth term is actually a times r to the n minus 1. It's not a times r to the n. So when I say we take the sum of the first n terms of a geometric series, of a geometric sequence, we're really summing a times r to the little n, as little n goes from 0 to capital N minus 1. Okay, and we derived the formula for this. We said that this is equal to a times 1 minus r to the n divided by 1 minus r if r is not equal to 1, and it's equal to a times n if r is equal to 1. Right? Now notice the notation here. I use little n or lowercase n to represent the index in the summation, and uppercase n is the number of terms in the geometric series that we are adding. Now, it may be a little bit annoying as to why I'm using a lowercase n and an uppercase n. I'm actually preparing you for what is common terminology in this course. Now, little n typically represents a time index for discrete time signals, and capital N typically represents the number of terms. So even though it may be a little bit annoying, you may have wondered, why did I not use I instead of little n, for example, right, lowercase n. But I think it's better to get used to this notation because this is what you typically see in books and for the rest of the course. Okay. Now, there are a few variations of this that will be important. So let's actually, before I do that, maybe I'll just work out a simple example just to make sure that we get this. Now, there are many examples in the homework, and I've made separate videos, worked out examples for many of them, so you can watch them separately. So let's take an extremely simple example. So suppose we have so here is the sum of how many terms in the geometric series. Think about that for a minute. That's sum of 11 terms of a geometric series, right? So the formula for this is A, which is in this case, first let's identify A and R. What is A? A is 1, R is 1/2. So R is clearly not equal to 1. So this part of the formula applies to the summation, and that tells us that the summation is 1 times 1 minus 1/2 raised to 11 divided by 1 minus 1/2. 1 minus 1/2 is, of course, 1/2. And this is some number that you can punch into your calculator to evaluate. Okay. There are many more examples. Like I said, I've separately worked out many examples, some of them where R is complex, so on and so forth. Now let's go back to this expression here, and let's look at two variations of this. Sum of infinite terms, or a geometric series with infinite terms. So what happens when capital N is infinitely large? So if this series continues to go on like this, what happens if we add all the terms in that series? Well, before you even use this formula to compute all of this, so think about what is going to happen. You are adding infinitely many terms in a series, right? Now, if these numbers keep on getting bigger, and notice every term in this series is obtained by multiplying the previous element by some common ratio. Now, if the common ratio R has a magnitude that's bigger than 1, what's going to happen is the magnitude of these terms keeps on increasing as you increase the exponent of R. So in that case, what's going to happen is when you sum all of them, that series is going to diverge, right? You cannot put a number to that series if you take infinitely many, the sum of capital N terms, and you let n become large. However, if the magnitude of R is less than 1, then these terms themselves are becoming smaller and smaller in magnitude as the exponent increases, and there is hope that if I sum all of them, the sum actually converges to something, right? And indeed, that's exactly what happens. So what we can do is we take this formula and let's think about what happens when n becomes infinitely large. So let's plug in n is equal to infinity in this, and let's see what might happen. So Sn, or S infinity, is going to be A times 1 minus, so this R to the n, what's going to happen to R to the n is either this is going to diverge if the magnitude of R is bigger than 1, or if the magnitude of R is less than 1, as n goes to infinity, what happens to R raised to n? That's going to go to 0. Right? So what's going to happen is we're going to get we're going to get 0 if the magnitude of R is less than 1, divided by 1 minus r, which is a over 1 minus r, if the magnitude of r is less than 1. If the magnitude of r is less than infinite, is greater than 1, then this becomes undefined, or it diverges. We can say it diverges if the magnitude of r is bigger than 1. Now, if the magnitude of r is equal to 1, well, then it might diverge, or it might keep on oscillating, or it might not converge to any number. In either case, if r is equal to 1, if the magnitude of r is equal to 1, this can become undefined. Okay, it will not converge to anything. So it converges in the case that the magnitude of r is less than 1, in which case we get a over 1 minus r. So to work out an example, if you take infinitely many terms of this geometric series, so instead of stopping at 1 over 2 to the 10, if we kept on going like this, then, so for this series S infinity will be a, which is 1, divided by 1 minus r, which gives you 2. And indeed, that's easy to verify. So if you look at 1 plus half, that's 1 and a half, 1.75, 1.875, so on and so forth. As you can see, it's getting closer and closer to 2. It's going to converge to 2, but it's never going to, so it's going to converge to 2 as you take more and more terms in this sequence. Another slight variation of the sum that you might see, or in fact a slight generalization of the sum that you might see, might look like summing the series or taking terms in the sequence starting from the power of r, which is n sub 1 to n sub 2. So this is a very general form. So as long as n2 is bigger than n1, we're going to define a formula for this. So what we can do to derive this formula is, there are a couple of ways to do it. One way to do it is to think of this summation as actually summation n starting from 0 to n2, a times r to the n, minus summation n starting from 0 but ending in n1 minus 1 of a times r to the n. And for each one of these, we can use this formula. So when I use this formula to compute this sum, we're going to get a times 1 minus r to the n2 plus 1. Notice that we get the plus 1 because if you sum up to n minus 1, then the power goes to n. So if you sum up to n, this should be n plus 1. So when I sum up to n2, it's r raised to n2 plus 1 divided by 1 minus r minus a times 1 minus r raised to n1 divided by 1 minus r, which you can see is a times r to the n1 minus r to the n2 plus 1 divided by 1 minus r if r is not equal to 1. And if r is equal to 1, we are simply summing. How many terms are we summing? Think about that for a minute. If r is 1, then you are simply multiplying a by n2 minus n1 plus 1. So this is the most general formula. I would like you to remember this formula. This is the one formula that I would like you to remember and be able to work with. Okay, there are plenty of examples that we are going to do in the class in separate videos, and I think it will be very useful to to get comfortable with this formula and be able to work. So of course, this formula is just a special case of this where we put capital N1 is equal to 0, right? So when I plug in N1 is equal to 0, I get 1. So I get A times 1 minus, and then if I plug in N2 is equal to N minus 1, I get exactly this formula over here. So this is the more general formula. So I would like you to remember this formula, and we can derive all these things from here. So if I set N2 to be infinitely large, then this term goes away, right? And then we get the sum to infinitely many terms, so on and so forth. So please understand this formula and be able to work with this formula.